In this lesson, we'll be determining if a function is even, odd, or neither. And once we know if a function is even or odd, we'll be able to use that to help us evaluate definite integrals. So first, let's review what even functions and odd functions are. First of all, even functions. An even function is a function that's symmetric about the y-axis. Next, we can test it. There's two different ways to test it. First of all is the test that always works for each kind of function. Is what you do is you can determine if a function is equal to when you plug negative x into that function. If it is, it's an even function. The last thing here says test for polynomials, and so if you have a polynomial, if all the exponents are even, then the function is even. So that's easy to determine. Down to odd functions. Odd functions have rotational symmetry about the origin. And then to test it, you do the same idea. You're going to plug negative x in, and if you get the exact opposite function, then the function's odd. And test for polynomials again, if all exponents are odd, then the function turns out to be odd. So those are the definitions of even and odd functions and tests for them. Here's how we're going to use that. First of all, if you want to test if a function is even or odd, if you know what the function looks like, if it's a familiar one, you can tell if it's even or odd by just thinking about the graph of it. If it has symmetry about the y-axis, then it's even. If it has rotational symmetry about the origin, then it's odd. If it's a polynomial, we can come down here. If it's a polynomial, you can use your knowledge of the exponents that we just mentioned. If all the exponents are even, it's an even function. If they're odd, it's an odd function. Now realize a constant is x to the 0 power, so that has an even exponent. And next, the last thing, number 3 here, it says if you're not familiar with the graph, or if it's not a polynomial, well, we can use the test here. And what you do is you plug in negative x into the function. So you put in negative x. You're going to simplify the function. Now, when you simplify the function, you're going to be using rules that you know. Maybe it's something squared, or maybe it's using some trig identities that we might know. But once you simplify it, if the function is exactly the same as the original, it's an even function. And after simplifying, if it's the opposite of the original, then it's an odd function. And if it doesn't fit either of those, then it's not even or odd. So what we're going to do now is look at several examples. Just determine if it's even, odd, or neither. So this first one, we can look at the function f of x equals x to the 4th plus x squared minus 6. Now realize this minus 6 is really x to the 0 power. And so all the exponents are even. And it's a polynomial, all the exponents are even, so this is an even function. So easy enough. Next one. Here we look at our exponents again. This is a polynomial, so we can look at our exponents. This is x to the 1st if nothing's written there. And we see that the exponents are all odd, so therefore it's an odd function. This one here, we have x cubed minus x to the 1st. And then remember this, if nothing's written here, this is x to the 0 power. So now we have an exponent of 3, an exponent of 1, and an exponent of 0. Well, they are not all odd, so this one is neither even or odd. So again, we're just, for all those, we just use that polynomial test. We get to this one here. This is not a polynomial, and we're probably not familiar what this function looks like. So what we want to do is we want to simplify, or we're going to do our test here, and we are going to plug in negative x for x. So instead of putting x, we're going to put negative x, and then we're going to try to simplify this. Well, in order to simplify this, we need to have a knowledge of some of our trig identities. So down here are our trig identities, and we see sine and tangent are both odd functions. If you plug in a negative, you get the opposite of the function. And so up here, we know that this, since we have a negative negative 2 pi x. So let's simplify on the inside first. We got negative tangent negative 2 pi x. Well, tangent is an odd function, so this negative, we have negative 3 times negative tangent of 2 pi x. It fits this identity right here. And so realize later on we'll be seeing maybe things with sine or cosine and being able to use those. And this gives us positive 3, because we have a negative times a negative, tangent of 2 pi x. And now if we compare this to our original function, they are opposites. So whenever we see that when you plug negative x in and you get the opposite, so this one was negative 3 tangent 2 pi x, and this is positive 3 tangent of 2 pi x, you know that it's an odd function. So we actually had to use the test in that one. Is f of x equal e to the x even, odd, or neither? Well, here we should be familiar with the graph of e to the x. E to the x is an exponential function. It has a horizontal asymptote here, so it comes up and looks like this. And as we look at that, that obviously is not symmetric about the origin or the y-axis. So just by looking at the graph, we know this is neither. So there's one where we can use the graph. Here's another one. This is e to a power, but this has a different power. It's just not e to the x. So let's go ahead and try our test here. We have, we're going to plug in negative x in for x. So we have e negative x squared. Well, we know that if we square anything, we're just going to get a positive. And so this is really the same as e to the negative x squared. And that is the exact same as our original function. So if it's the exact same, it's an even function. All right, g of x looks pretty complicated. We have x squared plus cosine x all over sine x. Not very familiar with what this graph looks like, so we're not going to look at the graph. So let's go ahead and try our test again. We're going to put negative x in for each value of x. So we have negative x squared plus cosine of negative x over the sine of negative x. Oops. Over sine, I wrote that wrong, sine of negative x. So let's use our knowledge here of algebra. Negative x squared is simply going to be equal to whatever x squared is. We looked at our trig identities before. We know cosine is an even function, so cosine of negative x is simply equal to just the cosine of x. And also, we talked about sine of negative x is the same as negative sine of x. So our numerator here is the exact same as our original numerator. The denominator is the opposite. Well, what we can do here is we can think, we can have a negative out here. We can factor out a negative 1 out of our denominator, and we have negative x squared plus cosine x over sine of x, and we see that is the opposite of what we had originally. So this, oops, and this are opposites, and so if they're opposites, we know it's an odd function. Now this last example here is kind of applying what we just learned to a fairly easy one. We want to evaluate this integral, this definite integral without a calculator. It goes from negative 1.5 to 1.5, and we got x cubed minus x dx. Well, we know this here is an odd function. So I'm just going to draw any odd functions, not necessarily this one, but odd functions, remember, are symmetric about the y-axis. And so an odd function might look something like this. That's supposed to go through the origin. And if we're finding the definite integral, we know this part above is positive and this part below is negative. But since it's odd, these are the exact same absolute value. This is just a positive and this is just a negative. So if we went from negative 1.5 to 1.5 in an odd function, those things are going to cancel each other out, and you actually just get that this is equal to 0. We don't need to know what this area is, and we don't need to know what this area is. We just know that they are opposites, so they'll cancel each other out. So the definite integral can easily be found if you know the function is odd, and it's 0. And so that's our lesson on even and odd functions, and then we can use those ideas to help us with definite integrals.